Yeah, we speak French. I do that. Me either. No, I like them. Oh my God. Me too.
Okay, so just as a reminder,
All right.
packet 6 for seniors are due on the 9th. There's also packet 5, but packet 5, we're gonna be able to spend that week, that first that EOC week, as well as the week after, to work through packet 5. There will be homework from packet 5, but I think we should get it done without any issue. This packet 6, we will have class time for packet 6, but I'm not gonna provide that class time until that first week of AP exams, and by then, you know, I think a lot of students will be in and out of the classroom. So I want to make sure that you guys get a head start on that. The key is on the website. I've also recorded videos for most of the problems. So and I'm sending out text reminds with the link as well as with the password for that page. So I encourage you guys to try to do 1 or 2 pages a day, so that even if it can't get through all of it by May, at least you have a good chunk of it done, and then the last 20 or so pages it won't take that long to finish up. Okay. So again, the purpose of packet 6 is so that you can have kind of exposure to multiple choice tests from previous years that College Board has released. But my main focus is just with FRQs. I feel like FRQs is free response questions are the ones that that students feel a little bit more shaky on. So just being able to work through, but also free response questions are more predictable in terms of we kind of know what type of questions will show up. With multiple choice, it's just a wide range of could be anything. But I think giving you guys a chance to see all those problems from packet 6 should give you a pretty good idea what an exam will look like. I'll go over this in more detail later, but if you look in side packet 3, that second page behind the cover page, I provided exam details. So you can look through it if you want. I will also spend time going over details and tips, probably a week or 2 before our AP exam. Okay, so we're going to try to just run through a variety of free response questions from packet 3. So the focus with this packet is particle motion, Riemann sums, and solving differential equations, but probably not going to do the solving differential equations until after the break. I want to focus mainly on Riemann sums, particle. Okay, so page 1. Okay, go ahead and read the problem, and then I'll follow up in a few minutes here. Okay, so number one, a car travels on the straight track during the time interval from 0 to 60 seconds. The car's velocity, measured in feet per second, acceleration are given. It's a continuous function. The table shows selected values of these functions here. So just want to kind of talk a little bit about what we can gather from this table. So at 0 seconds, the velocity is -20. So if it's moving along a straight track, that means -20 would mean it's going the opposite direction. And let's just assume that, it's like left versus right. So it's going the opposite direction. And then it's slowing down, and then eventually it stops, and then it starts moving in the positive direction. And then acceleration is increasing, but then decreases, and increases and decreases again. Okay, so part A, using the appropriate units, explain the meaning of the depth integral from 30 to 60 of the absolute value of v of t in terms of the car's motion. So we know that the integral of v of t is going to give us displacement. Displacement of position. But if we have absolute value around it, that's going to give us total distance, right? So here, this is going to be total distance. Doesn't matter, whether it's moving left or right. We're just counting everything as positive values. And then approximate using trapezoid approximation with 3 subintervals. So we're just basically going to go through table of values and adding up areas of trapezoids. But because this is absolute value, we're treating everything as what? As positive. Yeah. So everything is positive distance. We're going to pretend like all of these trapezoids are going to be finding us positive area. Okay. So we know that the integral from 30 to 60 is total distance traveled in that 30-second period. And then see if we can practice doing trapezoid approximation. So again, the formula for trapezoid is width over 2, or 1/2 width, and then times height 1 plus height 2. We can break up our intervals this way. 30 to 35 is one interval. 15 to 50 is the second interval. Sorry, 35 to 50, and then 50 to 60. So we started with velocity. If we accumulate velocity over the period of time, we're not going to be ending with feet per second. We're not going to be ending with feet, right? We're going to be able to know how much distance this car is going to travel back and forth. So 1/2 width, 1/2 times 5, and then we add the two velocity together. Again, we're making everything positive because of the absolute value. So 14 plus 10. And the second trapezoid, 1/2 times 15, 1/2 width. And then the heights are our velocity value, 10 plus 0. And then 1/2 width, 1/2 times 10, and then 0 plus 10. Okay, part B says using appropriate units, explain the meaning of this integral from 0 to 30 of a of t in terms of the car's motion. maybe this is hard to interpret, but what can we do to this integral from 0 to 30 of a of t to get it into a form that maybe we can recognize more? What can we do with that notation? Can we evaluate this? What can we make this change into? What do you know about the integral of acceleration? Integral of acceleration is what? What's one level above acceleration? Velocity, right? So we can just go through first theorem, right? We know that v of t, and then plug in the upper and lower bounds. So it's v of 30 minus v of 0. And then maybe it's a little bit easier to interpret this, right? What's v of 30 minus v of 0? What is that going to tell us? The change in what? Change in velocity over that time period, right? We know how fast the car is going at 30 seconds. We know how fast the car is going at 0 seconds. If we subtract it, we can figure out how much has changed in that 30 seconds. So it's change in velocity in that 30-second period. And to calculate it, we'll do v of 30, which is negative 14, minus v of 0, which is negative 20. We get 6 feet per second. So that means between 0 and 30 seconds, comparing those two velocities, this car would have changed by 6 feet per second between 0 and 30 seconds. Part C, between 0 and 60, can we guarantee that there's going to be a time when velocity equals negative 5? So anytime we see, oh, must there be a time, we know it's trying to ask us to guarantee a value. And when we try to guarantee a value, typically there's two ways of getting there, right? It's either IVT or mean value theorem, right? So I think IVT is easier to check for. So let's look at our velocity function. Look at our velocity values. Can we guarantee that our velocity value is going to hit negative 5 somewhere on this interval? Yes, right. We see negative 10 to 0. It's got to cross negative 5 somewhere. So that's IVT, right? We see a point below our target. We see a value above our target, and the graph is going to have to connect between those two targets or between those two values. So it's got to hit it. So that's IVT. So we can say, okay, we have 1 point below negative 5, which is coming from v of 35. And we have a point that's above negative 5, which is 0 on the other side of that endpoint of our interval, v of 50. So if we're going to land, if we're going to start at negative 10 and go to 0, we've got to hit negative 5 somewhere. Then IVT guarantees a time on that time interval where v of t must be equal to 5. Part D, on the same interval, or from our table from 0 to 60, must there be a time when acceleration is equal to 0? Acceleration equals 0. Well, if we look at our acceleration table, is acceleration going to ever see 0, or can we guarantee based off of our table? Right, we can't, right? So, but we don't want to just stop and say, okay, IVT doesn't apply. There's potentially another way, and that's looking at velocity, right? We know acceleration is the slope of velocity. Is there any place where maybe we can guarantee that there is going to be a slope of 0 somewhere on that velocity graph? What would it require if we want a slope 0 of velocity? We need two velocity values to be what? The same. Yeah. So do we see two velocity values that are the same? Yeah, we do, right? So the only way that our velocity can hit -20 and then go back to -20, it's got to eventually have a slope 0 in order to get from -20 back to -20, right? -20, -30, -20. It's got to hit slope 0 in between. And so because we can guarantee that there's a slope 0 on our velocity graph, we know there must be an acceleration of 0 as well, because we know acceleration is just the slope of velocity. Okay, so that's, you can either say mean value theorem or Rolle's theorem, but Rolle's theorem is specifically made for slope 0, but mean value theorem will also stand as well. But we have to state our conditions. Our velocity is continuous with brackets, differentiable with parentheses, and then because the endpoints are the same, we can guarantee that the slope is going to be 0 somewhere along that path. Or you can say by MVT, since V of 25 minus V of 0 over 25 minus 0 is equal to 0, then V prime of t is equal to 0. Either way, we are looking at the slope of the velocity level and showing that the slope is 0. Okay, number 2, page 2. Okay, read the problem for a minute, and then we'll look at it together. Okay, temperature of water in the tub at time t is modeled by a strictly increasing twice differentiable function. So this this graph is always increasing. Twice differentiable means a smooth curve. No holes, no asymptotes, no sharp turns. WT is measured in degrees Fahrenheit, and T is measured in minutes. At time t equals 0, temperature of water is 55 degrees, so we have some anchor measure to work from. The water is heated for 30 minutes, beginning at time t equals 0. Values of WT at selected values for first 20 minutes are given in the table. Okay, part A, use the data to interpret or estimate W prime of 12. Show the computation that leads to your answer. Using correct units, interpret the meaning of your answer in the context of this problem. So W prime of 12, that's derivative, but we don't have a function to find the derivative. So the next best thing is considering derivative as what? What's another word for derivative? What's the word that we associate with derivative? Slope. Yeah, slope. So we just are just going to find the slope at 12. And we don't have 12 available, so we'll just pick points closest to 12 and just do the slope. So just do change in Fahrenheit over change in temperature over change in time, and that'll give us our rate. Right? And we know that W prime of 12 is going to be the rate that temperature is changing on that 12th at that 12th minute. And then our units, what's our unit of measure going to be? Change in temperature over change in time, so degrees per minute, right? Degrees Fahrenheit per minute. Part B, use the data in the table to evaluate the definite integral from 0 to 20 of W prime of t dt. Using correct units, interpret the meaning in the context of this problem. So we don't have a W prime table in front of us, so we can't really add up the area under a W prime table, but maybe we can convert this into a different form. Is there a way to evaluate this? How would you evaluate the definite integral from 0 to 20 of W prime? What can we make W prime turn into? Integral of W prime will make it rise up to what? What function? Or let me ask you this. How would you evaluate the definite integral from a to b of f prime of x dx? What is turn into? Yeah, f of b minus f. Right? So this is first theorem, right? So therefore, the integral from 0 to 20 of w prime can also be impacted that way, right? We can make this turn into what? W of 20 minus w of 0. Now, if we had the graph of w prime in front of us, then we'll just rely on adding up areas. But because we don't have anything on w prime level, we can turn it into something that is usable because we have a table of values for w of t. So we'll just do w of 20 minus w of 0. What does that information give us? Right. W20 minus W0 is 71 minus 55. What does that tell us? What does that information tell us about our problem? So 71 minus 55, that ends up giving us 16. So 16 degrees. What does 16 degrees tell us about what's happened in this problem? The temperature has what? Increased, yeah. Temperature has increased in that 20-minute period. That's all, right? So it's a looks like a really complicated notation here, but all it's telling us is that temperature has increased 16 degrees. Sorry, 71 minus 55, 16 degrees in the course of that 20-minute period. Part C, between 0 and 20 minutes, the average temperature is 1/20th in an interval from 0 to 20 of WT. So use Lefferts-Riemann sum with 4 subintervals to approximate this value. Does this approximation overestimate or underestimate the average temperature of the water over the 20 minutes? So let's go through Riemann sums. Let's go through adding up rectangles, Lefferts-Riemann sum. So we're going to figure out what this value is and then divide it by 20. And that will give us our average temperature. But we want 4 subintervals. So see if you can go through width times height for each of your subintervals to add up your areas. But don't forget, we got to multiply by 1/20th or multiply by 1/20th. We got to have something that's in the temperature range, right? We don't want to have an answer that's in the hundreds because we're looking for average temperature. So it's probably going to be somewhere between 55 and 71 when everything is calculated. It's also asking, is this going to be an overestimation or underestimation? So here's what the graph could look like. It's an increasing graph, but we're forcing a Lefferts-Riemann sum. So if we're attaching the upper left corner, all these rectangles are going to be inscribed. They're all going to fall under the graph. So we know that because it's increasing function and a Lefferts-Riemann sum, we're going to be left with an underestimation, right? The area of these rectangles is going to be lower than the actual area under the graph. Width times height. So that 60 degrees should make sense, right? We have lowest is 55, highest is 71. It makes sense that our average is going to land somewhere between those two numbers. All right, part D, between 20 and 25 minutes, the function W models the water temperature, has a first derivative given by W prime, which 0.4 root T cosine of 0.06 T. Based on the model, what is the temperature of the water at time T equals 25? So we only have the temperature up to that 20th minute. After 20 minutes, they're giving us W prime, which is a formula that we can use. And we can think about maybe involving this formula, our final value equals initial plus displacement, right? We know that we're looking for temperature at the 25th minute. We have the temperature at the 20th minute. and we're trying to bridge that gap between the 20th and 25th minute. We have the rates at which the temperature is changing. So if we can accumulate that rate in that 20 to 25th minute, then we can use that accumulation to add to what we've gathered on the 20th minute. So if I want to find the temperature of the 25th minute, we'll take the temperature of the 20th minute and then bridge that gap using the formula, using W prime. Because we know that if we accumulate W prime over the 5-minute period, we're going to actually achieve the change in temperature in that 5-minute period. So if we know how much the temperature changes in that 5-minute period plus the temperature of the 20th minute, we can add those together to figure out what the actual temperature is at the 25th minute. Okay, I'll have you guys try number 3 on your own. Let's look at number 4. Read number 4 and see if what we've done so far begins to look more familiar in terms of, oh, like they're just asking a different variation of the problem that we just did, and see if things become, more familiar now that we've seen, something similar to it. Okay, so read page 4. Okay, read the problem. See if you can do A and B. Okay, velocity of a particle moving along the x-axis is modeled by a differentiable function. Estimate the acceleration of the particle. So we know acceleration is the rate of change of velocity, so we can just do slope, right? Slope of velocity will give us acceleration, and we know our units will be meters per second per second. Pick the closest t values to 36, so we'll choose 40 and 32. Part B, we know the integral of velocity. Integral will make velocity rise up to position. So it's x of 40 minus x of 20. And what that means is it's the particle's change in position, right? It's displacement. And then we can turn around and also use the table to find our area. So we want to use trapezoids. This time we do want to hold on to our negative values since there's no absolute value. So 1/2 width, height 1 plus height 2. And it's okay for our displacement to be negative. That just means that we end up to the left of where we started. Between 0 and 40 seconds, must the particle change direction in any of the subintervals indicated by the table? If so, identify the subinterval and explain your reasoning. So we can just tell by looking at the signs, right, that the particle must change direction if we see a sign from positive to negative, right? +5 to -10 velocity means it's moving forward and it's moving backwards. And then from -4 to 7, we also see another change from going from left to moving right. So yeah, we should be able to just look at the table and make that conclusion. It doesn't mean that there's no additional change in direction. It's just based off of our data. This is the least that we can say, right? That there's a guaranteed change in direction between 8 and 20, and a guaranteed change in direction between 32 and 40. There may be more, but our data, our limited data is only supporting a guaranteed 2 changes. Okay, part D. Suppose the acceleration of the particle is positive. So if the acceleration is positive, that means my velocity is always going to have a positive slope, right? Acceleration is the slope of velocity. Explain why the position of the particle at 8 seconds must be greater than x equals 30 meters. Well, we know that anytime we want to look for position, we can just think in terms of final equals initial plus displacement. We know that x of 8, we know x of 0 starts off at 7, right? 7 meters. And let's assume that between 0 and 8, he's traveling at the minimum 3 meters per second the entire way through. That's the worst case scenario, right? Worst case scenario is he's holding steady at the same velocity all the way up to that 8th minute. Now, if we draw that graph, we see that the area is going to be 3 times 8, which is 24. And 24 plus 7 is 31. So worst case scenario, based off the table, if he's moving at the slowest possible speed, which is 3 meters per second, he's going to end up at 31. And 31 is definitely greater than 30. So, and we know that his velocity is never going to dip below 3. So If that's the slowest that he goes and he starts at 7, he's going to at least end up at 30, which is to the left of 31. So since x of 8 is greater than equal to 31 and x of 8 is greater than 30, right? We see that the graph is definitely above that. So that area is definitely going to part B. Yeah, it must be greater than 30 because we're getting 31 already. So that area of the square is already 31, or that range is already 31, and because our graph is higher than that, we must achieve greater than 31. Okay, so your homework, pages 1 through 5. I'll send out a reminder, and then tomorrow we'll try to get through page 6 through 12. All right, come get your phones. I'll send out a reminder this afternoon. And the key is attached to the back of your packet.